So we left the last video on something of a cliffhanger. Is the converse to theorem 3 true? So is it necessarily the case that if for arbitrary sets A, B, and C, if we know that A union C is a subset of B union C, can we conclude that A is a subset of B? We could try to draw a picture here. We've got these sets A, B, and C, and we know that A union C is a subset of B union C. So draw them all like this. A, B, and C. We know that A union C is a subset of B union C. Here's B union C here. Okay, which would have to mean that there's nothing kind of out here, because if there was stuff out here, then that would be that. It wouldn't be the case that A union C was a subset of B union C, because there'd be this element out here which was in A union C but not in B union C. So we really need this whole area here, this that I'm shading purple, to be empty. But does that necessarily mean that all of A lies within the B circle? No, not necessarily, right? The rest of A could all lie within the C circle instead. So this sort of suggests to us that I'm not entirely convinced by the Venn diagram that this is going to be the case. And so what would it mean to show that the converse is false? Well, we'd have to give a counterexample. So we'd have to come up with some sets A, B, and C that satisfy the hypothesis, that make it true that A union C is a subset of B union C, but do not satisfy the conclusion. A is not a subset of B. So let's try and think about what those sets could be. I need to design these sets in such a way so that the first statement's true, but the second statement is false. So in particular, if A is not a subset of B, I need to make sure that there's at least one element that's in A but not B. Let's call that element 1. Maybe A has some other stuff. I'll throw like a 2 and a 3 in here. And I'm going to put that 2 and 3 here also. Let me just add some more stuff too. I'm just playing around with it. I don't necessarily know what I'm trying to do yet. But now I need to make sure that whatever my C set is, it makes it true that A union C is a subset of B union C. All right. In particular, A union C is going to include, at the very least, the elements 1, 2, and 3. And I need those 3 elements to also appear in B union C. Now, since 1 doesn't appear in B, I better put 1 in C to compensate. So how about, let me add 1, 6, and 7. It doesn't really matter. You don't actually even need any more stuff in C here. But now it's true that A union C, which would be the set 1, 2, 3, 6, 7, is in fact a subset of B union C, which is a set 1, 2, 3, 4, 5, 6, 7. Okay, so this hypothesis is true, but the conclusion is not, right? A is not a subset of B. And that's because we found an element that's in A that's not in B. Because 1 is an element of A, and 1 is not an element of B. Okay, this shows that the converse of that statement was false. Cool. All right, now the last thing that we're going to do before we get on to practicing this stuff is talk about some set theoretic properties. These are statements that you could prove. You have the tools. You could go ahead and prove each one of these using the same techniques that we've been going over in this last video. There's a whole bunch. I'm going to post these notes. Don't feel the need to copy them all now. But it's good exercises, it's good practice to try and prove these sorts of things. Like, we proved number 9, we proved the first part, that if A is a subset of B, then A union C is a subset of B union C. But you could also conclude that A intersects C is a subset of B intersects C. And you'll notice that a lot of these properties are similar to what we proved for statements in chapter 1. Like, we proved that OR statements are commutative, that P or Q is logically equivalent to Q or P. That's similar to saying A union B is equal to B union A as sets. And in fact, those properties for statements that we proved in the first chapter are exactly how you can justify these properties here for sets, including De Morgan's law at the bottom. I'm not sure if you can read that. Okay, so as an exercise, you might want to go through and do some of these. We might do some in class. We're going to prove one of these distributive laws now, using, like I said, using exactly those laws that we saw for statements. So we're going to show that for arbitrary sets A, B, and C, that A union B intersect C is equal to A union B intersect A union C. So essentially what this is saying is this distributes sort of in a funny way. A union B intersect C sort of distributes to A union B intersected with A union C. Okay. Now, normally you would prove one set is equal to another by proving first that this is a subset of this, and then vice versa, prove this is a subset of this. But I'm going to do sort of the shortcut way where we prove things using if and only if statements. So proof, it's going to look like I'm proving the first subset relationship, but really I'll be using if and only if statements, so it'll work backwards as well. So we're going to let X be an element of A union B intersect C. Okay, well by the definition of union, this means X is an element of A or X is an element of B intersect C. But definitions are if and only if statements. So this is true if and only if. Sometimes it's easier to shorten this to IFF for if and only if. This is true if and only if X is an element of A or X is an element of B intersect C. That's by definition of set union. And now, using the definition of intersection, I can unpack this second statement as well. So this is if and only if X is an element of A, or, let me put it in parentheses, X is an element of B, and X is an element of C. This is by definition of set intersection. All right, now I got to try and unpack it into something like this. So if you wanted to, you could break this up into two cases. Case 1, X is an element of A, explain why it has to be in the second set. Case 2, X is an element of this. Except this is really why we did all that work in chapter 1, to show that the distributive property for statements is true. The distributive property for statements says that P or Q and R is logically equivalent to P or Q and P or R. Go back in your notes, it's there somewhere. They're logically equivalent, they have the same truth table. I can apply that here because this is really a statement of the form P or Q and R. And so this is going to be true if and only if P or Q is true. So X is an element of A, or, write it in words, or X is an element of B. Okay, and P or R. X is an element of A, and X is an element of C. Oh, sorry, or. Right, this is by the distributive property for statements. So I've saved myself a lot of work of thinking through the cases just by applying those properties that we proved in chapter 1 about statements. Now that I have this, I'm basically done, right? Because for X to be in A or X to be in B, that means it's in the union of A and B. And for X to be in A or X to be in C means X is an element of A union C. This is, again, by definition of union. All right, and finally, putting together these two statements that have an and in the middle, by the definition of set intersection. This is if and only if X is an element of A union B intersected with A union C. That's exactly what we were trying to prove. And because we were using if and only ifs along the way, we don't have to go backwards, right? This if and only if means X is an element of A union B intersect C, if and only if X is an element of A union B intersect A union C. Thus, we're done. A union B intersect C is equal to A union B intersect A union C. Right? So it'd be a good exercise for you to actually go back and try to do some of these proofs for these other commutative associative laws. See if you can use those laws that we have for statements to really easily be able to prove one thing or the other using the laws for, or to prove these laws for sets. This one actually we already did in a previous video.